All right, so for the three-man water balloon or three-person water balloon launcher, gotta be, make sure my questions are not biased, but um, you have like the two wires or the two strings or elastic bands are 140
30
degrees
degrees
apart.
apart. Right.
So for the diagram for that, I think that's question 3.
Right.
Yeah, you if you have one of the strings be along the origin, um, and that would be at 0 degrees, then the tension in that string would be pulling on the bucket. The bucket would kind of be at the origin,
Okay.
um, and then one of the strings is pulling along that origin. Looks like I used a different reference frame. I used minus 70 degrees
Right.
be my
And
my
290.
one, and plus 70 would be the other. And then at zero, the resultant of those two would be at 0 degrees. So I think I have the spreadsheet. I can open that up. And so yeah, you can choose any number of coordinate systems. Like probably the more common choice is to put the first tension along the x-axis and then the second one at 140 degrees. And then what you're thinking of, the resultant force in that case would be along 70 degrees, but the equilibrium is the force that has to cause them to sum to 0. So that's it's kind of like I guess a
So how
different.
does that work in the spreadsheet? Like I said,
Yeah,
I got the right magnitude, but
yeah, the equilibrium is programmed. It's slow to open, of course. My computer's been crawling lately.
yeah, mine is just old. Period.
Yeah, mine was it was new for a while. Now it's getting old. Here we go. Close a few windows. Of course, the act of closing those windows then slows it down. All right, now I didn't want a blank workbook. It's trying to make me open a blank workbook. Wait, here we go. Now this will open. Okay. So if you had, so for my diagram on here, the way I have it drawn, I have one of the tensions. Both of these are 60 pounds in magnitude, and the direction to T2 here is minus 70, and the direction
Okay.
to T1 is plus 70.
Because
All
you know
right.
what I use for that? Where you have minus 70, I use 290 because I just went, you know what I'm saying? Because it was counterclockwise is positive.
Yeah.
So I just came all the way around.
Yeah, that's
Instead
absolutely
of saying
right.
it,
Yeah.
I made it 290.
Yeah. So watch this. Look, see my X and Y components there of 20.52 and minus 56.38. If
Right.
I change this to 290, they don't change. It recalculated, but they stayed the same because 290 and minus 70 are equivalent to each other. They're 360 degrees apart. So since they're the same direction, they calculate the same components.
Okay.
So that's a good point. It's correct either way.
All right.
And then notice the 70. You can see there's a reflection across the x-axis. Like these x components are both the same, but the y component for T1 is positive and the y component for T2 is negative. And you can see that for the 290, it has a negative y component, and for the 70, it has a positive y component. They're equal and opposite.
Right.
So the two y components actually sum to 0, and then the two x components are equal. They sum to be 41.4 pound or zero point zero 0.04 pounds. So
Right.
that actually works out to be the resultant. And when it recalculates the direction, it's basically at 0 degrees there. But you'll see now the equilibrium, that's this value over here. That's actually set up so that it's 180 degrees off of the resultant. Now somebody had contacted me and said that the one in the instructions said plus 180 and that the one in the example had minus 180, and whether you add or subtract 180, it's the same direction ultimately, but whether it reads positive 180 or negative 180, it's still the same direction in space. So like a lot of these little, differences that cause confusion sometimes are people realizing that the same instruction can give you two different results, or two different angles will give you the same result if they happen to be 360 degrees off. But with your angles, you're going to get, so now my equilibrium in this case is 41. So the direction of the third force, this equilibrium by definition is the force it would take to balance out the other two. And it's actually worked out to be exactly opposite, equal in magnitude to the resultant. So notice I just have the resultant magnitude equal to the equilibrium magnitude, but then the equilibrium direction is simply off by 180. So it's basically the exact magnitude and direction that cancels out the resultant, which in turn, if you get the resultant sum of those two forces only, and you know that the third force, F3, is balancing them out, that third force is the equilibrium. So in most cases, people give the resultant there, not realizing that they needed the force that's opposite the direction of the resultant, which is the equilibrium. But that's what the answer is. The force required to keep the bucket at rest is the equilibrium that you could read directly off the spreadsheet. Now, for a different coordinate system, if you
for this problem, there is no direction.
For the equilibrium.
Yeah.
Yeah, that's to the right of so the magnitude and direction are in two different cells. So this is the resultant direction. Theta XR is the angle counterclockwise from the x-axis of the resultant. And the resultant of those two vectors is 0 degrees. Now let's say I use a different coordinate system. Let's say I took my first angle and I put it at 0 degrees and my second one was at 140. Then the resultant would be exactly where you were thinking, towards 70 degrees in the middle. See that? So it's the same magnitude, but now it's at 70 degrees. The problem is identical. I'm just using a different coordinate system. So if I had a coordinate system where the x-axis ran parallel to T2, the y-axis would be perpendicular to that, and then T1 would be up in the negative y direction. Now, let me see if I have a pen and paper. I can draw exactly what I'm talking about. I'll be right back. I do have a paper here. Just gotta grab a pen. Sorry if you said anything. I didn't have the headphones in.
No, I didn't say anything.
Okay.
I'm just looking at some of the write up here under number 3, and you get the 41 magnitude, but it comes up with minus 110. Where is that value coming up at?
All right, I'll show you. So that's actually minus 110. If you take 70 degrees and you subtract 180 from it, you're going to get minus 110.
Oh, okay.
Okay, so just drawing this up right now. All right, so let me stop my screen share. And I'll hold this up. Okay. So if I take my 260 degree forces there, and the two vectors are drawn there with the 60 next to them.
Yeah.
And that angle is 140. And you can see my x-axis, that's off to the right there. And my y-axis is vertical.
Correct.
I don't know if I have that on the screen. But then the one is at 0 degrees and the other's at 140. Okay, so the resultant, that's going to be bisecting that, but the equilibrium's going to go down opposite that direction. So if you take your x direction and you rotate counterclockwise.
Oh, that's why it has to be minus 180.
Yeah, that would be 70 degrees minus 180 is exactly opposite.
It's the other side. It's the other side.
Yeah. Yeah, so the minus 110, you would rotate 90 and then an additional 20 degrees, and that's where the minus 110 comes from. All right.
Yeah.
So it's kind of like seeing that coordinate system on there and then not thinking of an angle as a vertex to a shape, but thinking of an angle as a number of degrees rotated. You can rotate, the positive direction of rotation is counterclockwise. If you
Correct.
rotate clockwise, it's negative rotation. All right. So yeah, you can use any number of, I've had people also, one of the more common coordinate systems I get as well is, go back to sharing the screen. I also get one where the T1 is kind of at, like positive. They'll put it so the y-axis bisects it, and you have positive 20, positive 160, and the resultant is at 90 degrees. The equilibrium's at 270 or
Right.
minus 90. So if you just, as long as the two vectors have 140 degrees difference between their two angles, you can really choose an infinite number of coordinate systems. But probably the more common ones are the ones where the resultant, because people kind of intrinsically know that if you pull back on a slingshot, as long as it's symmetric, you're going to have an even, like the angle is going to be, here you have 90 degrees is your angle for the resultant, and then the equilibrium's at minus 90 or 270, depending on whether you add or subtract that 180 degrees. So I mean, if you add the 180, then you get about 270 there. And the only reason it's off by like a half a degree or 5/100ths of a degree is because of the, I think here, yeah, I used an approximate value for the tangent.
Yeah.
So rather than using that pi function, and that was actually one of the questions I think on the handout was, what function can pi replace, or what can it replace in the spreadsheet? That's the pi function. That gives you the true value of pi rather than this approximate value.
Right.
But for this first question, that's the default angle measurements for Excel are radians, and we measure angles in degrees. At least most people think more in terms of degrees with angles. So that converts degrees to radians, multiplying by 2 pi and dividing by 360. So that's just a conversion. There's also a square root function. So these development questions are more about the model building, which I actually probably should have just not asked those questions because they are a little bit more confusing mathematically than the actual vector ones, but the vector ones are pretty confusing. So was there other ones that you had questions on?
No, because that's as far as I got last night when I was doing it. My only other question is, um, going back just to clarify, what we have to turn in.
Yeah.
Like, for example, let's just go with like number one. So,
Okay. Let me open up number one then,
yeah,
just for the benefit of people that watch the video.
let's just start with number one.
Okay. So for
So,
go ahead.
so we would first we would answer the question. Now, do you need a cut and paste of the actual spreadsheet numbers
No, I
for
don't need
coordinate
that.
answers?
I figure if you can if you can produce the magnitude and direction of the resultant,
Right.
then that shows that you knew how to work the spreadsheet. But
All
I
right.
would
So
want to see the diagram drawn. This is drawn as a free
that's what
body
I want to know.
diagram.
So we would need the XY axis diagram for each one of these.
Yeah, everyone should have a coordinate system. It doesn't have to be built over top of it. You could just have a little XY like in the upper right corner. But I think it helps to have those reference lines on your diagram for pulling the angle.
Okay. So what's the picture on the other side to the right?
This is demonstrating how if you place the vectors head to tail, that it'll give you this resultant. Because when we add these vectors, the four tens at these four angles, I'll show you the resultant. So we have 10 at, I think it was 94, 113.
181, 225.
All right, perfect. So then the resultant magnitude and direction are in G2 and H2. So
Right.
24.7 at 151 degrees would be the magnitude and direction of the resultant. Now think about 24.7. That's like 2.5 times one of those vectors magnitudes. All right, so now when I look at this picture, one of those vectors is 10, right? Any one of them is 10. So that's about 2.5 of those vectors there. That's where the 24.7 magnitude is. And the direction, 151 degrees, is the amount of angular rotation counterclockwise from the x-axis. So if you want to be able to visualize what the resultant looks like, you can place the vectors head to tail. But if you want it to be easier to kind of approximate the angle of each vector, draw it coming from the origin on a coordinate system, and you can pretty easily tell this is 90 plus an additional 4. A is 94, and then B is 113,
Right.
C is the 181, and D is the 225.
So we don't need that other diagram. You don't need both of them.
No, you don't need that. But
Okay.
you could do one or the other, as long
Okay.
as you have a vector diagram on there. Because sometimes, like for displacement vectors, it makes more sense for problem 2 to show like one then the next in succession like that, because that's how displacement vectors kind of happen. They happen one then the next. But if you're talking like force vectors, force is all simultaneously acting on a single point, it makes more sense to do a free body diagram, which is a force vector diagram. So like when you're diagramming forces on an object, you draw them all coming from the same point, and that point represents the object. But when you're talking about a kid walking along the beach, they walk 75 meters, then they walk 30 meters, and that's how those those vectors are more, I guess, reasonably represented as being drawn head to tail. So it's really a preference thing. I don't have a particular preference, which is why I drew some of the diagrams as free body diagrams and others as head to tail.
Okay.
But the hardest part really is producing the vector diagram from the words, and then inputting the vectors, assigning a coordinate system and inputting the vectors. Like I showed how you can have two different possible reference frames here, or two different points of view with the same problem. So it actually makes it hard, because I was a little bit ambiguous with the kid walking along the soft sand. Like it doesn't say north or south, and whether the ocean was to the east or west. Like it's just kind of walking along. You could have the kid walk in two different directions.
Right.
So now the one that's probably the trickiest is the goal seek one. And that just depends on how you look at it. So let me show you how to do that one. And then anyone who watches the video will see how to do it too. That's the dog collar designed to send a mild electrical shock. My brother actually has a dog, one of those fenceless, things in his yard. And the dog sometimes just chases a rabbit and just busts right out. He's willing to take the shock to go after the rabbit. But this is a story kind of hits close to home for him. But it says like, okay, at 30 meters away from the sensor. So I guess it's assuming the sensor is a circle. And once you hit a resultant of 30 meters, the dog gets shocked. So if the dog runs straight away at 15 meters, you can make that along the origin, and then turns at an angle of 40 degrees. So that's actually diagrammed for number 5 here. I'll open that up, show the diagram. All right, so the first displacement is 15 meters along D1. And then a 40-degree turn is actually almost kind of running in the same direction. It's not, it would be a 140-degree turn if the dog cut back this way and ran along that line. So it's meant to be just like a slight turn to the left
Yeah,
there.
he just veered to the left.
Yeah, and the instant the dog's going to get shocked is when the resultant hits 30 meters along that line. So basically, it's a trial and error on the second displacement. In this case, in any case you would use goal seek for is if you know the answer, but you don't know the value of one of the input values. So it kind of works the spreadsheet backwards. So if for a normal problem, you would input the values over here. In this case, we have 15 meters at 0 degrees if you make your x-axis along that first displacement. And then we have an unknown magnitude at 40 degrees. Oops, not 4 degrees, 40 degrees that produces a resultant magnitude of 30. So I always tell people just guess on that first one. And if you guess and say, all right, what happens if the dog runs 10 meters? Did the dog get shocked? You would check in cell G2 to see if that was at or greater than 30. And then it just becomes a guess and check. You change this number until you see that that number is 30. And you can do that manually if you just kind of start zeroing in on it and realize, all right, you just got to get bigger and bigger. But, if you get too big, then you're past that point. So the question's like, where is the dog stop exactly? That's what you do goal seek for. And it's under data and then what if analysis. It's kind of buried.
Yeah.
But you're basically telling it to set just exactly what you do when you do guess and check. You're checking for this cell to be a value of 30 by changing the cell you're guessing in. And then when you say, okay, the computer just tries different values in that cell until it gives you the value you're looking for in that cell. And then you know that the dog had to have stopped like just shy of 16.9 meters. So that would be the answer for.
Square. What if it's a square?
What if the yard is a square, you mean?
Yeah. But
Well,
for this problem, I don't want to get to that. This problem is a
yeah.
circle.
Yeah, for this problem it's a circle. And that's
Okay, that's
I
fine.
got the
That's
yeah.
fine.
I mean, if it was like if you had exact known dimensions, that would actually make it a little difficult for a different thing, for something other than a circle, because the resultant, the distance from the origin is a certain amount that works out to be a circle
Right.
for a radius of 30 meters. So that's where I say use goal seek, set G2 to 30 to value of 30 by changing the cell. So really, I'm just kind of guiding everyone through and getting them to where the input values are just about what you'll need to see. Like on number 4, you'll have to realize like this angle should be minus 30 degrees when you input, or minus 35 degrees,
Right?
whatever the angle is. It would be a negative angle there because, or if it's 45 degrees, it would be 315. You just have to make sure you're that's probably the hardest part of these problems is coming up with the correct angle to put in for theta, because usually the magnitudes are provided there. All right.
Yeah.
So yeah, there's some good things you can do. Like you can do like swimming problems. Like I'll do, when I do it in class, I'll do like Michael Phelps is swimming across a river, and the river has a current of 4 meters per second to the east. So I'll make 4 and 0 degrees east will be the x direction. And then if he swims at 3 miles per hour, I think that's or 3 meters per second. That's a reasonable speed for, top level swimmer. Then what at to the north at 90 degrees, what's his resultant magnitude and direction? And you get the direction is this way, and stuff like that. So there's all types of different problems you can ask. That's how they do navigation in the ocean. If you know the direction of the current, know the direction you're headed, they can calculate your resultant path, in magnitude and direction, and then kind of track where you are in space with coordinates. But you got to know like velocities and times you're going at those velocities and directions and stuff. So navigating in 2 dimensions, a little bit complicated, but nowadays we have GPS to help us with that stuff.
So G and H is our answer.
You said G and H.
Yeah. No, I mean on the
Oh
spreadsheet.
yeah. G2 and H2 are the
Right,
resultant magnitude and direction.
right.
But in some cases, like question 3, the equilibrium is actually the answer, and question 6, that's like what does the hiker have to do to get back to the starting point? So the resultant is starting point to ending point. The equilibrium will be ending point back to starting point. So the equilibrium is I2 and J2, and that's just 180 degrees opposite the resultant. It's the same magnitude, just inputted exactly as being equal to the magnitude, but then the equilibrium direction is 180 degrees off the resultant direction.
Yeah.
All right. So yeah, if
And
you go through those, you should be able to work your way through. The other thing, some people ask with number 7 what to actually do with number 7, and that's basically just add those 3 vectors. I think it says determine the resultant sum of those 3 vectors. But these angles that are given, the big mistake on number 7 is people just input 65, 55, and 70. You don't want to do that. You need to compute the theta sub x value because they all have the same x axis that's pointing to the right. So you got to do the math to see, like, this is 180 plus theta sub c is the direction for C, and then 180 minus theta sub B is this one. So you need to calculate those angles based on those given reference angles, what actually gets inputted in the spreadsheet. You know what I'm saying? So you have like these, zoom in a little bit. Theta A, theta B, and theta C are given
right.
in reference to axes that are not the positive x-axis. You have to get the angle rotated counterclockwise from the positive x-axis to input into the spreadsheet.
So so you need to know the amount from X to A and then the amount from X to B
Yeah,
clockwise.
yeah, exactly.
And
Every
then do
angle
you
you
go all
input.
the way around or do you go negative when you get to C?
Well, you
Like
basically
with
just
that, go ahead.
take
With
like a
that,
needle, like a second hand that's pointing in the x direction, and then how many degrees does it need to rotate to point in any one of those directions? So for theta A, it's just whatever that magnitude of that angle is. But for theta B, you'd have to rotate through that much. And for theta C, you'd have to rotate past 90, past 180, down to like 200 something for theta C.
right,
Theta B is between 90 and 180.
right.
So it's the angle counterclockwise from the x-axis for each one. All right. Any other questions?
Yeah, I think that's enough confusion for now.
Yeah, it's confusing, but all right, I'm gonna stop the recording because I think we got some good stuff on there that should answer a lot of questions for people.
Yeah.
I got a lot of thank yous from the last.